Don Smith Capacitor Energy Method by Joel Lagace. Introduction. Understanding the Don Smith Capacitor Energy Method, unlocking hidden energy potential. Energy is everywhere. It surrounds us in forms both seen and unseen, waiting to be harnessed. From the vast electromagnetic fields of the Earth to the latent potential within everyday components, the universe brims with untapped energy that remains largely overlooked by conventional systems. If we can learn to use energy more efficiently, with a focus on unconventional methods, we might unlock pathways to extraordinary advancements in power generation and utilization. This publication aims to explore one such approach, the Don Smith Capacitor Energy Method, an intriguing yet enigmatic system that hints at how energy can be manipulated in ways beyond traditional expectations. Throughout history, pioneers in alternative energy have challenged the boundaries of standard science by rethinking how components behave in unconventional configurations. Figures like John Bedini demonstrated how inductors, capacitors, and other circuit elements could be used in non-standard ways to produce novel results, often aligning with what mainstream science dismisses as impossible. These inventors dared to experiment with what was considered fringe, offering glimpses into energy systems that defy the inefficiencies of modern power grids. Don Smith, like Bedini, left us with fragments of a larger puzzle, provocative demonstrations and tantalizing hints that challenge conventional interpretations of energy transfer, high-frequency behavior, and resonance. One of Don Smith's most fascinating contributions to the field of alternative energy systems lies in his public demonstrations of what can best be described as a one-wire energy transfer system. Using a high-voltage, high-frequency setup, Smith demonstrated how a capacitor plate could charge another plate at a distance, seemingly without any direct electrical connection between them. He referred to this as a mirror effect, figure A, wherein energy appeared to transfer or reflect itself across space. Most intriguingly, he claimed that if you wanted to extract current, you could simply ground the second, or mirror, plate, completing the circuit in an unconventional way. Yet Smith never fully explained this process, leaving much of the inner workings shrouded in mystery. Instead, he often showcased slides of various high-voltage generators, Tesla coils, capacitors, and transformers, hinting at the tools necessary to achieve these effects but without detailing how they all fit together. He even claimed that a single 1F capacitor could produce 1 kilowatt of power, a bold statement that invites deeper scrutiny but lacks sufficient explanation. Figure A, Don Smith Capacitor Demonstration. The goal of this publication is to go beyond Don Smith's surface-level hints and delve deeply into the technical principles underpinning the energy phenomena he demonstrated. We aim to explain how these energy gains might occur from a well-grounded perspective, leveraging both traditional laws of physics and theoretical insights that extend those laws. By exploring high-frequency, high-voltage interactions, resonance effects, electrostatic coupling, and unconventional electromagnetic field behavior, we will piece together a clearer understanding of how systems like Don Smith's could work. Along the way, we will explore the possibilities of tapping into the vast, unseen reservoir of energy all around us, unlocking potential applications that could reshape how we think about power generation and consumption. Let us begin this journey into the heart of the Don Smith Capacitor Energy Method, a journey into a world where energy reveals itself in ways we are only beginning to comprehend. We will follow the clues left by Don Smith and build upon them with rigorous exploration and technical insights. Could his methods hold the key to unlocking untold energy efficiencies? Let us find out together. Chapter 1, The Driving Circuit, Charging the Capacitor. At the heart of Don Smith's public demonstrations lies a critical yet often misunderstood element, the driving circuit, the device that quickly and efficiently charges the capacitor, setting the foundation for the rest of the energy system. Whether it was during a lecture or a live demonstration, Don Smith would often dazzle audiences with high-frequency, high-voltage devices, showing various resonance systems that appeared to combine Tesla-like principles of energy transfer with capacitive charge-discharge mechanisms. Observers would eagerly focus on the interplay between coil A and coil B, scribbling notes about their construction, connections, and placement, hoping to replicate what they believed was the magic of his system. But here's the catch: the capacitor doesn't care how you charge it, as long as the driver stage is suitable. This misunderstanding has led many down the wrong path, chasing illusions of magic transformers instead of grasping the foundational principles of the driving circuit itself. Don Smith's demonstrations frequently highlighted a variety of methods to charge capacitors, ranging from simple, straightforward designs to more elaborate and efficient setups. In some cases, he would use traditional neon sign transformers and STs, stepping up the voltage and then driving a high-frequency oscillation. In others, he would demonstrate Tesla coil-like systems with high Q, high-quality factor, resonance, emphasizing energy transfer through tuned circuits. At times, he would showcase high-voltage capacitive plates being charged through what appeared to be electrostatic coupling. The sheer variety of charging methods gave the impression of complexity, and many assumed that every coil, transformer, or circuit configuration he displayed was a critical, irreplaceable piece of the puzzle. Figure B, simplified Don Smith driver stage. However, the truth is more straightforward. Don Smith seems to have been demonstrating different ways he had discovered to efficiently charge large capacitors, each method suited to a specific purpose or efficiency goal. From simple power supplies to intricate high-voltage systems, the underlying principle was the same: find a way to inject energy into the capacitor with as little loss as possible. The focus on his demonstrations often overshadowed the fact that the charging method itself, while important for efficiency, is not necessarily the key to the energy gains he implied his system could produce. A closer look reveals that the real magic does not lie in the driving circuit or the capacitor's charging process, but in what happens after the capacitor is charged. Don Smith often left this part conspicuously absent in his explanations, instead directing attention to his custom transformers and coil configurations. This omission has led to a common misconception among experimenters that the extraordinary energy output he claimed must somehow come from the transformer configuration alone. Many who attempted to replicate his systems, running loads directly off their high capacitance, high voltage setups, found themselves disappointed, often concluding that Don Smith's claims were exaggerated or outright false. This frustration stems from a misunderstanding of what the driving circuit is meant to achieve. The capacitor is not a power source, it is an energy storage and transfer medium. The driving circuit's purpose is simply to charge the capacitor efficiently, regardless of whether that's done with a simple DC power supply, a Tesla-like resonant coil system, or a modern high-frequency, high-voltage driver using advanced solid-state components. The focus on exotic charging methods has obscured the real question: how does Don Smith's system transduce additional energy into the system after the capacitor is charged, allowing it to deliver the claimed power gains? In this report, we aim to clear up these misconceptions by shifting the focus to the parts of Don Smith's system he left unexplained. While his driving circuits and charging methods are interesting and important for efficiency, they are not the source of the extraordinary energy gains. The real question lies in what happens after the capacitor is charged, specifically in the coupling mechanisms and transduction processes that may allow additional energy to enter the system from the environment. This is where we must direct our attention to uncover the missing piece of the puzzle. In the next chapter, we go back to basics. We will dive deeper into these coupling mechanisms, exploring how capacitors, coils, and high-frequency resonant circuits might interact to produce unexpected results. By peeling back the layers of Don Smith's demonstrations and examining the system from a grounded yet open-minded perspective, we hope to reveal the technical principles behind what he only hinted at. The key to unlocking the potential of his methods lies not in the driving circuit, but in understanding how energy flows and amplifies within the broader system. Let us begin to unravel this mystery together. Chapter 3, Back to the Basics, the Physics of Energy Redistribution Between Capacitors. Let's explore what happens when you take a charged capacitor and connect it directly to an uncharged capacitor. This is a critical exercise to understand how energy behaves in traditional systems, laying the foundation for exploring more advanced energy configurations like those demonstrated by Don Smith. Scenario setup: Precharging capacitor A. Imagine we have capacitor A, which is charged to 10 volts. Let's assume the capacitor has a capacitance of 10 microfarads. The energy stored in any capacitor is calculated using the formula: energy equals 1/2 times the capacitance times the voltage squared. For capacitor A, the capacitance is 10 microfarads and the voltage is 10 volts. Let's calculate the stored energy. First, square the voltage. 10 volts squared is 100. Then, multiply the capacitance by 100. 10 microfarads times 100 is 10,000 microjoules, or 0.001 joules. Finally, divide by 2. 0.001 joules divided by 2 equals 0.005 joules, or 5 millijoules. So, capacitor A starts with 5 millijoules of energy. Connecting capacitor A to capacitor B. Now, we take capacitor A, charged to 10 volts, and connect it to a second, identical capacitor, capacitor B, which starts uncharged. Capacitor B also has a capacitance of 10 microfarads. Once connected, charge redistributes between the two capacitors until they reach the same voltage. See Figure C. Figure C, capacitor dynamics. Why does the voltage equalize? This happens because of charge conservation. Charge moves between the capacitors to equalize the voltage across them. Since both capacitors are identical, the charge splits evenly, and the final voltage will be the average of the two initial voltages. Capacitor A starts at 10 volts, and capacitor B starts at 0 volts. The average of 10 and 0 is 5. So, after the connection, both capacitors will end up at 5 volts. Energy after redistribution. Now let's calculate the energy stored in each capacitor after the voltage has equalized at 5 volts. The formula for energy is the same. Energy equals 1/2 times the capacitance times the voltage squared. For each capacitor, first square the voltage. 5 volts squared is 25. Then, multiply the capacitance by 25. 10 microfarads times 25 is 250 microjoules, or 0.00025 joules. Finally, divide by 2, 0.00025 joules divided by 2 equals 0.00125 joules or 1.25 millijoules. Each capacitor ends up storing 1.25 millijoules of energy. Since there are two capacitors, the total energy in the system after redistribution is 1.25 millijoules times two capacitors equals 2.5 millijoules. Where did the energy go? Initially, the system had 5 millijoules of energy stored in capacitor A. After redistribution, the system only has 2.5 millijoules. Half of the energy is gone. Why does this happen? The missing energy is not destroyed, it is dissipated as heat during the redistribution process. Here's why. 1. Resistive losses. In a real circuit, the wires and internal parts of the capacitors have some resistance. As charge moves between the two capacitors, the flow of current through this resistance generates heat, which dissipates energy. 2. Electromagnetic radiation. Even if there's no significant resistance, the movement of charge can cause the system to oscillate, similar to how a spring bounces back and forth. These oscillations can produce electromagnetic waves, which radiate energy away from the system. 3. Internal losses in capacitors. Real capacitors are not perfect. They have internal resistance and dielectric losses, energy dissipated within the material of the capacitor, which also contribute to energy loss. Why this matters in advanced systems. When we think about Don Smith's devices, this example highlights why focusing solely on the capacitor's charging process is not enough. Simply charging and discharging capacitors in a traditional way results in significant energy losses. The energy gains Smith implied in his systems must come from additional energy sources or coupling mechanisms that offset these inherent losses. Chapter 3 continued, the dynamics of energy redistribution and reclaiming the lost energy. In the last section, we saw how half the energy is lost when a charged capacitor, capacitor A, is connected directly to an identical uncharged capacitor, capacitor B. After the connection, the charge redistributes and both capacitors equalize at half the original voltage, leaving only half of the initial energy in the system. This loss of energy is primarily due to dissipation during the redistribution process, and in a normal circuit, it seems irreversible. However, there's an intriguing possibility if we start to think outside of traditional circuit behavior. What if we introduce a control process, such as flipping the polarity of one capacitor? This opens up a fascinating way to reclaim the energy that is otherwise wasted, and it challenges the limits of what we normally think capacitors are capable of. Let's break it down step by step. Why can't we simply send the energy back? In the standard setup, where we connect capacitor A, charged to 10 volts, to capacitor B, uncharged, charge redistributes until both capacitors settle at 5 volts. At this point, 1. Capacitor A has half of its original charge and is now at 5 volts. 2. Capacitor B has gained charge and is also at 5 volts. The total energy remaining in the system is half of what we started with. But why can't we send the remaining energy in capacitor B back to capacitor A to restore it? The reason lies in charge redistribution dynamics. If you connect capacitor B at 5 volts back to capacitor A also at 5 volts, there is no voltage difference between the two capacitors. Without a voltage difference, there's no driving force to move charge between them. The system is in equilibrium, and no further energy transfer can occur. This is why, in a traditional circuit, we can't recycle the lost energy. It's already dissipated during the initial charge redistribution. The game changer, flipping the polarity of capacitor A. Now let's introduce a twist. What if we use a controller process, e.g., a solid-state switch H-bridge or similar mechanism, to flip the polarity of capacitor A? This means we reverse the orientation of its voltage, making its positive terminal negative and its negative terminal positive. By doing this, something fascinating happens. Step-by-step dynamics. 1. Initial state kappa at -5 volts, cap B at +5 volts. After flipping the polarity of capacitor A, it is now at -5 volts while capacitor B remains at +5 volts. This creates a voltage difference of 10 volts between the two capacitors, since -5 volts on cap A and +5 volts on cap B result in a potential difference of 10 volts. 2. Discharging cap B back into cap A. When we reconnect the two capacitors, with cap A flipped, charge flows from capacitor B back into capacitor A. This is because capacitor B now has a higher potential, +5 volts, compared to capacitor A, -5 volts. The flow of charge causes capacitor B to discharge completely to 0 volts, transferring all of its stored energy back into capacitor A. 3. Final state kappa at 0 volts, cap B at 0 volts. After the transfer, both capacitors are at 0 volts. The key insight here is that capacitor A now holds all the energy that was previously in capacitor B, even though capacitor A ends up at 0 volts. How does this work? Where does the energy go? Let's look at the internal dynamics of this process. 1. Energy in capacitor B. Capacitor B starts with 1.25 millijoules of energy from the previous redistribution step. As it discharges into capacitor A, this energy is fully transferred into the circuit. 2. Capacitor A's role. When we flip the polarity of capacitor A, we effectively give it the ability to absorb energy from capacitor B by creating the necessary voltage difference, 10 volts. This allows all of capacitor B's energy to flow back into the system, but with a twist the energy is redistributed in such a way that capacitor A ends up with zero net charge after the transfer. 3. Final energy transfer. The energy from capacitor B is now effectively stored in capacitor A's electric field and circuit interactions. Capacitor A is left at 0 volts, but it has effectively absorbed the full energy of capacitor B's discharge. Why is this process so interesting? This process is extraordinary because it shows how clever manipulation of charge and polarity can allow you to reclaim energy that is otherwise wasted in normal circuits. By flipping the polarity of one capacitor, we 1. Break the equilibrium. Flipping the polarity creates a new voltage difference, allowing energy to flow again between the capacitors. 2. Reclaim lost energy. The full energy in capacitor B, which represents half of the system's original energy, is transferred back into the system, effectively recovering energy that is typically lost as heat or dissipation. 3. Enable full discharge. Capacitor B is discharged completely to 0 volts, which wouldn't normally happen in a traditional setup. This enables its full energy to be used. Implications for advanced energy systems. This process hints at how non-standard energy pathways can be exploited to recover or enhance energy transfer in electrical systems. In normal circuits, the focus is on stability and efficiency, but processes like flipping polarity challenge conventional thinking by introducing controlled instability. This technique could form the basis of advanced systems that 1. Recover lost energy. By carefully managing the flow of charge and flipping polarities at key moments, systems could recover energy that is typically lost during redistribution. 2. Enable energy amplification. If combined with external energy inputs, e.g., resonance effects, environmental energy sources, or electromagnetic coupling, these methods might amplify energy transfer beyond what is possible in traditional setups. 3. Utilize energy storage in cycles. Flipping polarity opens up new ways to cycle energy between components, maximizing the use of stored energy in capacitors or inductors. Final thoughts. This polarity flipping process is a simple yet profound demonstration of how energy transfer dynamics can be manipulated to reclaim or enhance energy flow in electrical systems. While it doesn't violate the laws of physics, it highlights opportunities to sidestep the limitations of traditional circuits. By introducing deliberate control mechanisms like flipping polarities or using resonance to inject energy, we can explore new realms of energy efficiency and possibly even over unity systems with output greater than input by tapping exter. Chapter 4: The problem with traditional energy transfers. Let's start by revisiting the basic capacitor to capacitor energy transfer, like the one in Chapter 3. 1. Initial setup. Capacitor A is charged to 10 volts, holding 5 millijoules of energy, while capacitor B is uncharged. 2. Direct connection. When capacitor A discharges into capacitor B, charge redistributes until both capacitors are at 5 volts. The result: each capacitor now holds 1.25 millijoules of energy, for a total of 2.5 millijoules. The other 2.5 millijoules are lost due to resistive heating, electromagnetic radiation, or irretrievable oscillations. Where displacement current fits. In the traditional view, this 2.5 millijoule loss is simply written off as inefficiency. But what's really happening is that during the redistribution, a transient current flows through the connecting wire. This current is accompanied by a rapidly changing electric field in the capacitors, which generates a displacement current. Displacement current doesn't involve the movement of real charges like electrons. Instead, it arises from the changing electric field between the plates of the capacitors. This displacement current creates a magnetic field just like a real current, and that magnetic field can be harnessed. In most systems, this displacement current is ignored. It dissipates as heat or electromagnetic radiation. But what if we capture it? The advanced setup: harvesting displacement current. Now let's modify the basic capacitor system by introducing a transformer primary coil in the discharge path. This allows us to harvest the energy associated with the displacement current. Here's the step-by-step process, including how displacement current is harnessed to achieve 100% efficiency. Expect about a 10% loss in real life. Figure D. Displacement current. Step 1. Initial discharge, kappa to cap B. 1. Starting conditions. Capacitor A is charged to 10 volts, holding 5 millijoules of energy. Capacitor B is uncharged. 2. Discharge path with transformer primary. When capacitor A discharges into capacitor B, charge flows through the primary coil of the transformer. The rapid redistribution of charge generates a real current in the wire. A displacement current inside the capacitors due to the changing electric field between their plates. This displacement current induces a magnetic field in the transformer, which generates a voltage pulse on the transformer's secondary winding. 3. Energy transfer to cap C. On the transformer's secondary side, a rectifier charges capacitor C2 5 volts using the voltage pulse. This captures 1.25 millijoules of energy, the same amount that would normally be lost in the redistribution process. Result after step 1. Capacitor A and capacitor B are each at 5 volts, holding 2.5 millijoules of energy. Total. Capacitor C has been charged to 5 volts, storing the 1.25 millijoules of energy that would otherwise have been lost. Step 2. Polarity flip and reverse discharge. 1. Flipping capacitor A's polarity. Using a switcher controller, we flip the polarity of capacitor A, setting it to -5 volts. Capacitor B is still at +5 volts, creating a potential difference of 10 volts between the two capacitors. 2. Reverse discharge cap B to cap A. When capacitor B discharges back into capacitor A, now at -5 volts, the same process occurs. A real current flows through the transformer primary. A displacement current is generated as the electric fields in the capacitors change. This creates a second voltage pulse in the transformer secondary, which charges capacitor C again to 5 volts. Result after step 2. Capacitor A and capacitor B are now both at 0 volts, fully discharged. Capacitor C has been charged a second time to 5 volts, storing an additional 1.25 millijoules of energy. Energy accounting, 100% efficiency. After completing both steps, let's account for the energy in the system. 1. Initial energy, start of step 1, hollow circle capacitor A starts with 5 millijoules of energy. 2. Final energy, end of step 2. Capacitor A and capacitor B are fully discharged, 0 volts. Capacitor C is now charged to 5 volts twice, meaning it holds 2.5 millijoules plus 2.5 millijoules equals 5 millijoules total. Key observation. The entire 5 millijoules of energy from the original charge on capacitor A has been transferred to capacitor C. No energy was lost as heat, radiation, or oscillations. This represents 100% efficiency in energy transfer, minus traditional losses in the wire, etc. Why this works? The process achieves 100% efficiency because it captures the energy associated with the displacement current pulse during each charge redistribution. Instead of letting this energy dissipate into the environment, it is harvested via the transformer and stored in a secondary capacitor. In a traditional system, displacement current generates transient magnetic and electric fields, but these are typically wasted. In this advanced system, displacement current is actively harnessed to recover energy that would otherwise be lost. Displacement current is the key. This system highlights the critical role of displacement current. 1. It completes the energy loop. Displacement current ensures that the energy transfer is continuous even in the absence of real charge carriers between the capacitor plates. 2. It enables energy recovery. By leveraging the magnetic field induced by displacement current, we can transfer energy to other parts of the system like capacitor C without needing additional input energy. 3. It creates a feedback mechanism. Each displacement current pulse adds energy to the secondary circuit, allowing for repeated energy recovery during each charge-discharge cycle. The takeaway: efficient energy recycling. By incorporating a transformer into the discharge path and flipping the polarity of one capacitor, this system allows for 100% recovery of the original energy. In essence, it turns what is traditionally seen as an inefficiency, displacement current, into a powerful tool for energy recycling. This is where Don Smith's work offers inspiration. While he often spoke in incomplete or crude terms, his ideas about displacement current and one-wire energy transfer align with the principles demonstrated here. He hinted at how displacement current could be used to extract energy from high-frequency, high-voltage systems. Ideas we're now exploring in a rigorous, grounded way. Why doesn't the primary feel the secondary load? In this chapter, we explore a unique and unconventional feature of this system, the fact that the transformer primary does not feel the load on the secondary winding in the traditional sense. This behavior challenges the usual expectations of transformer operation, where any load on the secondary creates a corresponding load on the primary due to mutual inductance. Instead, in this system, the energy transfer between the primary and secondary windings occurs in a transient, time-dependent manner, driven by displacement current pulses. This decouples the secondary from the primary in a way that bypasses the traditional feedback loop of conventional transformers. Let's dive into why this happens and why it's so important for achieving near minus 100% energy efficiency. 1. How a conventional transformer operates. In a traditional transformer, the primary winding generates a magnetic field when current flows through it. This magnetic field links with the secondary winding via mutual inductance, which induces a voltage in the secondary. When a load is connected to the secondary winding, e.g., a resistor or capacitor, current flows through the load. This creates a secondary magnetic field which opposes the primary magnetic field as per Lenz's law. This opposition creates a back reaction on the primary winding, increasing the input power required to drive the primary. This coupling between the primary and secondary ensures energy conservation but also makes the primary winding directly sensitive to the load on the secondary. The more power drawn by the secondary load, the more work the primary coil must do. 2. Why this system is different. In this system, the energy transfer mechanism fundamentally differs from the steady-state mutual inductance of a traditional transformer. Instead of continuous energy transfer, the transformer operates on transient displacement current pulses that occur during the dynamic redistribution of charge between capacitors. This creates a decoupling effect where the secondary winding doesn't create the usual feedback loop on the primary. Here's why. A. The role of displacement current. Displacement current is not a real current like electron flow, rather, it's a phenomenon that arises from the changing electric field in a capacitor as charge moves. When charge redistributes between capacitors or when their polarities are flipped, the electric field between the plates changes rapidly, generating a transient displacement current pulse. This pulse creates a magnetic field which induces a voltage on the transformer's secondary winding. B. Decoupling via transient energy transfer. The displacement current pulse is time-dependent. It exists only during the capacitor charge equalization process when charge flows between capacitors A and B or during the polarity flip. Unlike steady-state magnetic coupling, this transient energy transfer doesn't establish a continuous feedback loop between the primary and secondary. C. No continuous mutual inductance. In a conventional transformer, the magnetic field generated by the secondary coil, when loaded, interacts with the primary coil, creating the back reaction that makes the primary feel the load. In this system, the primary coil doesn't experience this back reaction because the energy transfer happens in discrete bursts, displacement current pulses, rather than through steady-state coupling. 3. Why the primary doesn't feel the secondary load. Here are the key reasons why the primary is decoupled from the secondary in this system. A. The energy source is displacement current. The energy transferred to the secondary winding comes from the displacement current pulse, which is tied to the changing electric field during capacitor charge redistribution. This pulse is independent of the primary's continuous current flow. As a result, the primary winding doesn't experience the usual feedback loop caused by a secondary load in a traditional transformer. B. Transient nature of the pulse. The displacement current pulse occurs only during specific events. 1. When charge redistributes between capacitor A and capacitor B. 2. When the polarity of capacitor A is flipped and charge flows in reverse. Once the charge redistribution is complete, the displacement current ceases and the associated magnetic field vanishes. This prevents a steady-state interaction between the primary and secondary windings. C. Decoupling from steady-state mutual inductance. In a conventional transformer, continuous magnetic coupling ensures that any load on the secondary creates a proportional back reaction on the primary. In this system, the transient and localized nature of displacement current pulses decouples the secondary load from the primary. The primary sees the transient electric field change, but this is momentary and doesn't persist long enough to create a feedback loop. 4. What makes this system efficient? This decoupling mechanism plays a critical role in achieving the high efficiency of this system. Here's why. A. No energy loss in the primary. Because the primary doesn't experience the usual back reaction caused by a secondary load, it avoids resistive losses and inefficiencies typically associated with traditional transformers. B. Efficient energy harvesting. The displacement current pulse represents energy that is normally wasted, e.g., as heat or electromagnetic radiation in a conventional capacitor system. By introducing the transformer, this energy is captured and transferred to the secondary side, where it can be stored or used. C. Energy recycling. Filled circle. The polarity flipping and reverse discharge process allows the same energy to be cycled through the system multiple times. Filled circle. Each cycle generates a new displacement current pulse, which can be harvested independently, dramatically improving energy recovery. 5. Implications for advanced energy systems. This decoupled energy transfer mechanism has profound implications for advanced energy systems. 1. Transient energy harvesting. By leveraging displacement current pulses, the system recovers energy that would otherwise be lost in traditional capacitor discharge processes. 2. Efficient energy recycling. The ability to recycle energy multiple times within the system enables near -100% efficiency under ideal conditions. 3. New possibilities for energy systems. This system demonstrates that energy transfer doesn't have to rely on traditional steady-state mutual inductance. Instead, transient field dynamics can create new pathways for efficient energy harvesting. Conclusion: displacement current is a game changer. In this system, the transformer primary doesn't feel the load on the secondary, because the energy transfer is driven by transient displacement current pulses rather than continuous mutual inductance. This decoupling allows for highly efficient energy recovery with minimal losses in the primary winding. By harvesting energy from displacement current pulses, this system achieves near -100% efficiency, turning what is normally seen as wasted energy into a valuable resource. This unique approach offers exciting possibilities for developing advanced energy systems that challenge the limitations of conventional designs. Chapter 5: Recovering 100% Energy in Theory. Clever manipulation.